All right, welcome back. Today on the bench, we had a customer send in a Rev 6. And the customer's complaint was, I was wondering if you can repair that is a burnout component. I have 3 running on a Meanwell LS600, and one showed it would not connect to the pool when it viewed it remotely. Started it twice and would not connect, but was running. When I physically looked at it, there was a VR overtempeler on the screen. I unplug it for about 10 minutes, plug it back in, and the VR and the attached pick smoked a little, and then the PSU shut down. Okay. PSU will not power on. 2 other monitors work fine. Okay. So we got a Rev 6. Let's go ahead and take a look at the different view here. All right. So this is appears to be a solo Satoshi. Rev 6. I can always tell just because of the quality of the components, the type of coils that are used. I'll give you an example. Well, I don't have one handy, but high quality thick board, nice, dense. This is a solo Satoshi version. Okay. All right. So his complaint was this VREG right here. Now, if I change the angle on this, you can kind of see how that VREG is actually swollen up. You see the nice flat here, and then boom. Pretty common to see this on any of these devices where we don't have a fuse. So what happens, and we typically see this on customers that run Meanwells or other aftermarket power supplies that are much higher current rated. So let's say I want to run 3 devices. I run a Meanwell, like an LRS12 600, where I can run multiple devices off one power supply. Makes a lot of sense. However, the downside to that situation is that when these things are running, if one of these are your CSDs or your VREGs here, okay? If one of these goes short, which is what's happened here, it will draw the maximum amount of current that power supply can put out before tripping. So if this thing's humming along and this CSD decides to short, this is, let's say that power supply, and I can look up the specs, but that power supply will put out, let's say, 50 amps. Well, this thing is going to draw as much as it possibly can until either this burns until it's open, or the power supply recognizes that there's a problem and faults. This is a situation where this miner was running and then the CSD shorted. Without a fuse on this board, it will supply it as much as these traces and this component will handle. We don't see this on the Rev 5.1s. Here's just a scrap one I've got here. But like say here, right? This has got an 8 amp fuse in it. This will draw, if this happened on the whiteboard, this would draw until it got to just over 8 amps. It would open that fuse and it would stop. It would shut it down and prevent this level of damage. But that is not the case here with this design, with having no fuse on the board. And the most common fault on the pluses, on all the revisions, with this power circuit design is these CSDs, these MOSFETs, whatever you want to call them. These are the voltage regulators. So these pulse, which is provided by the TPS, comes from the logic of the LilyGo, pulses these 3 CSDs. These are all in parallel. It pulses them, input of 12 volts, output of whatever the voltage is that we want to provide to our ASIC. So 1150 millivolts is, I think, what the default value is. So they will output 1150 millivolts based on the pulsing that occurs within these. So if this shorts, then you can imagine it's 12 in, 12 out, but it's that full current. On the other side here, we have the coils, subcapacitors for the output ripple, and then it ultimately goes to the ASICs. And the ASICs, like any microprocessor, acts like a short. If I were to check this circuit, which I'll do right now, knowing that our CSD is shorted, I'm going to check across positive and negative. Here and here, and we have 0.1 ohms. So we plug in any power supply to this right now, it will trip the power supply, 100%. Because it's going to see a short for one and an immediate ask for pretty much everything that power supply can put out. And that's what's happened here. So like I said, we always see this when we have a customer that uses a third-party power supply that is high rated in amperage. Again, Meanwell, great product. Don't fault them. The device asked for as much power as it would possibly send because of this short, and it gave it everything it could until it finally decided it was done. And again, this happened while the miner was running. So if we were to plug in a Meanwell to this now, it wouldn't just start smoking. The Meanwell would see that it's shorted and it would say, nope, stop, we're going to shut down. But when it's in operation, it went from, send me 6-8 amps to send me all the amperage you possibly can. And that's what happens. Now, the big concern here with these boards, and when this happens, is, am I going to be able to get this off? Remember what I said, this is our input 12 volt side here. So these 6 pins here are all, when you take this off, matter of fact, I'll show you the back side of a CSD, what it looks like. You can see that these are all the same pad. Okay, so if you have bridges here, not a big deal because these are all the same. It's essentially all bridged underneath the chip. So we got 12 volts in, and we've got whatever our requested output voltage is based on cycle rate of the chip. Okay, but you send that much amperage through these little contacts. Soldering is a chemical bond that conducts electricity. We get that so hot, we will actually arc between these pads, the actual pad itself. Here, let me pull a new one out. I'll show you what a new one looks like. We buy all of our CSDs directly from Texas Instruments. Typically, depends on how many we need to buy. But we try to get the newest batch possible. So here's a brand new one. And these metal contacts will weld. And if this welds to these traces, I will most likely not be able to get it off without destroying the board. Because what will happen is I'll try to get this up and off, and it will be welded, and it will try and take this entire pad with it. Now again, these carry normal operation, they carry about 7 amps. Roughly, I'm using a rough number here, default values. So it's really difficult. It's not that it's impossible, but it's very difficult to reconstruct these traces and have a reliable power connection here. That's difficult. So what I'm going to do, the customer has sent this in for evaluation. And what we're going to do is we're going to see if we can get it off without destroying the board before I quote the customer on the replacement of the VREG, because if I can't get it off, it's kind of a moot point for the customer, and I'll advise him. So I'll let him know. When the customer left his hardware on here with his plastic spacers, those will melt. So let's get those off first, if I can get them off. There we go. And we're going to see if we can get this off and hopefully save this board. And if I can get it off, I'm going to immediately put on a new one because I've already got the board heated up. I try to limit the number of times I heat up a board if I don't have to. So I could heat it up, and then I've already gone through the motion. And I'll advise the customer, hey, this is what it needs, this is what it took to repair it, this is what the charge is. And if they don't want to proceed, I'll just take it back off. Not a big deal, but if I'm in here and I'm already heating it up, we'll take care of it. If I just had a shorted CSD and I could identify it through voltage injection, then I would do that and advise the customer on what the price is to fix it. So let's get this in focus for you guys. And we're going to see if we can't get it off. All right, I'm going to put my spacer on here, or my shield, not spacer, excuse me, my shield, to try and protect these. I actually remove, you can see here the fan header. I remove the plastic on the fan header because that's likely going to melt, and I just want to avoid melting those, and otherwise I'd never have to replace the entire fan header. And then I use this shield to help protect the display header as much as possible. So we're going to heat this board up to about 400 C to try and get some heat into the board so that when I hit it with the hot air, I'm not having to spend as much time heating that board up and blasting it with heat. So we're going to let this warm up, take about 4 or 5 minutes, and then we'll be right back. All right. We're back. So our board's up to about 400 C. Now these are all, say all, clear, most of these are made with lead-free solder. I just actually worked on one today that was not, surprisingly. It was made by our friends across the pond, and it was not lead-free solder. So getting up to 400 C, I was able to manipulate most components with almost no additional heat, which told me everything I needed to know. Not good, but okay. So these are definitely lead-free. So I'm gonna come in, and I'm gonna heat up right in between the two VREGs here, as you can see. I heat up basically here. Get some heat into this board and see if we can't get this VREG to come loose. Trying to keep the heat directed away from the shield and the header for the display, and also away from the electrolytic capacitors, because they do not want direct heat on them. They'll pop, but I also don't want to melt them. So heat it up right between these two VREGs. All right, let's see if we can get this thing to move. Got it. All right, we're able to get it off. That's a good thing. And then, like I said, I don't see any signs of arcing, which is great news. Great news for the customer. So I'm going to jump right on this while I've got it hot. Now I'm going to install a new VREG. So I come in with a little bit lower melting temperature lead-free solder. Again, this is a chip quick, lead-free. I add more to the pads. I get this bad boy lined up. Drop that on, and then I'm going to come back in with some heat. And what we're looking for is that chip to sit back down, lay back down. And because I just had a bunch of heat into this, should happen relatively quickly. Yeah. If you look closely, well, it's hard to see with this chip. I can show you on another chip another time, but it'll push out the solder like we see here, and it sits nice and flat, and you see the pulsing a little bit on the left side of there, the chip, that pulsing of the flux. That tells me that chip is sitting all the way down, and that looks really good. So I'll turn my hot plate off. I will take my shield off. I say hot plate, it's more like a board heater. Let's kick my soldering iron on. Let this cool down a little bit, and then I'm going to come in with some flux. We'll take a look at the chip I took off here in just a minute after we're done. While my soldering iron's heating up, it's almost done. You know, again, we got very lucky that I was able to get that VREG off. I've seen some of these that I've got pictures of ones that were so bad. I mean, as I'm heating them up and trying to get them off the board, it is lifting that trace off the board. It's just, I just stop. I don't even go any further. I just stop, send it over to the customer, picture it to a customer, advise them, and then that board's pretty much trashed. Like I said, you can probably there's probably some pretty creative people out there that can rebuild that trace, but and do it. And I rebuild lots of traces, but the amount of amperage that carries, it's pretty risky that it's going to hold up. All right. Okay, that looks good. I use a little bent tip on my soldering iron. And like I said before, the last 6 traces on these CSDs are all one bridge underneath, basically one big pad. But I try not to have any bridging at all. Sometimes it's harder on those traces than others. Okay. That looks really good. Let's, I'm actually gonna put a dab more flux here because I wanna see that. That looks really good. But I want to make sure this thing isn't twisted a little bit. It kind of looks like that side of the chip is down. Let's take a look. And what I'm looking at here, let's see if we can. Sometimes it's easier to see this with flux. Yep, that's exactly what's happened. Okay, so this chip is just a little twisted. And I don't like that, but you see how it's connecting at an angle all the way down? So let's realign that. Let's get that sorted out. All right, let's get that back on there. Get some heat back into that. It just, when it sat down, instead of straightening out, it was twisted just a little bit. And I'm not gonna leave it that way. So let's heat it back up. There we go. That's better. All right. Just make sure we don't have any other chips out of alignment. We're good. All right, that looks pretty good. That looks much better. That's what we want to see. Okay. So we will a little bit of flux. That's better. Okay. Same treatment as before. We're going to hit it with the soldering iron. As soon as it gets up to temperature. Looks good. Flux is your friend. Perfect. Everything's off there, perfect. Let's pull this excess flux off here. This board cooled down. While we're doing that, I'm looking for solder balls. Now we added solder paste, like I mentioned before. We do that to get a better contact patch on that CSD. But what you gotta watch out for is stuff like this. These little solder balls. It's a little easier to do this when the flux gets a little drier. Right off on the fingertip. It's amazing how small that is. Couldn't do this without a microscope. I don't see any more. That looks really good. Okay. Just trying to dab up some of this excess flux while it's still hot. Cleans a lot easier when it's hot. Now I could leave this flux on here. This is a known, what they call a no clean flux, which doesn't mean you don't have to clean it. What it means is it will not corrode the board or other components on the board. So I could leave it. I won't. I can't do it. I can't stand the way it looks. It just, yeah. I try to keep things looking as good, if not better, than when I started. As you can imagine, I go through a lot of Q-tips. There are many ways to do this. This is just the way I prefer to do it. It fits my style of doing this work the best. Perfect. All right, so I'm gonna pull this off the hot plate. We're gonna set it down on the silicon mat. And then we're gonna let it cool naturally. I'm not gonna do an accelerated cooling. So we're gonna give it a couple minutes and then we'll be right back. All right, we are back. Got her cleaned up. Pretty good. It's now back to room temperature. We'll do some final cleaning. Well, it's a little bit more touch up here. I'm not going to be able to get all of that stuff from the nooks and crannies, but a pretty good portion of it. And then we'll take a quick look to see if we are... Short is gone. And we are at climbing into the mega ohm. So short is gone. That's a good thing. All right. Here's what we're gonna do. I am going to take and mount a heatsink on it, so support the board. All right, sorry, child that needed something. All right, let's get this cleaned up. We'll get our test display mounted. I will put some thermal paste, just the right amount. That's all it takes. You don't need any more than that. Doesn't do any good outside of that silver area on the chip. Anything else beyond that is just waste. Okay. Fans on. I am not going to screw this down. I'm just going to set this heatsink on. Put light pressure. I usually work it back and forth just to get it seated on here. Just looking to make contact. And then I'll connect it up. And we're coming alive. First thing we see is 1.2 volts. That's the, I like to call it the look-ahead voltage that checks that output circuit. If that voltage is not there, or that voltage is too high during the startup process, it will prevent the TPS from firing on. Now we see that we're at 74 watts, 6.1 milliamps, or 6,100 milliamps, so 6.1 amps, and 1148 millivolts. The dashboard shows a 1.15 volts output. That's the output side on the VREGs. That's what it's measuring. And we are hashing. We're slowly gaining our hash up to our target of 4.8. So board came to me, completely shorted, no power on, no nothing. We looked at the VREG, we saw the damage. We swapped out the VREG, cleaned it up, and now we're back to hashing. We've hit our target. This board's hashing right where it needs to be. I'm going to let it run for at least 10 minutes. I want to make sure that my voltage regulator temperatures aren't too high, that I'm not over consuming. This particular board right now is consuming 77.4 watts at completely default. I always test these at default values. I don't know, customers don't tell me where they run them. It doesn't really matter to me. Default is kind of the standard that I'm looking for, especially with the varying quality of these devices that are out there. Some can achieve more, some can't. Some ASIC chips consume more power than others. It is a really shot in the dark, hit or miss. So I'm gonna watch this let it run for about 10 minutes, make sure everything looks good. I'm gonna reach out to the customer in this case and give them an estimate, or really tell them how much it is to change that VREG out, kind of give them the situation. And then we can go from there. Now, while that's running on my bench, I told you we would take a look at that chip that I took off. shed some more light on this. So this is the one that came off. Again, what they really should look like, and this is another bad one here, right? This is just flux on the chip. So nice flat surface. If we want to orientate these the same, we can see that buckle in there and how much that has raised up. You can even see the curvature. Oop. Yeah, got pretty hot, I would say. Carried a lot of load, but now let's take a look underneath. So the discoloration we see is really flux. But we are very, very fortunate that we didn't get arcing here and destroy the main board, which is we're very lucky. Unfortunately, I've seen quite a few of those, especially in the last 6 months, that have completely destroyed the board, and the board was pretty much scrap at that point. Trying to see if I have any other examples of this here. Oh, here's another one. I was lucky enough to get off. But they don't all come off. So I'll reach out to the customer. I'm sure he's going to be very happy we were able to save another one. Get him back up and hashing. I'll let this run for 10 minutes roughly, and then move on to the next one. Got plenty of them lined up, so we just keep on going. So if you need repairs, you can reach us at ixtech.xyz, very top of the website. Choose on the repair section, fill out the form, pay $25, mail it in, and we'll see what's going on. And we'll get back to you. I'll let you know. Appreciate you watching. Feel free to comment. If you get time, I answer those comments. But obviously we're pretty busy around here, so we can't always get to them right away. But we'll see you on the next video. Thanks.